So in this example, it looks like we have something that's in the form 0 over 0. We've got tan x minus x, which as x approaches 0 will be tan of 0 minus 0. So we got something that approaches 0 on the top, and of course x cubed will approach 0 on the bottom as well. So it's in the 0 over 0 form, so let's go ahead and apply L'Hopital's rule. So the derivative of tan x minus 1 in the top will give me secant squared minus 1. And then the derivative of x cubed in the denominator will be 3x squared. Okay, so there we just applied L'Hopital's rule. Notice that it's still in the 0 over 0 form, right? Because we still have this expression, secant squared x minus 1 over 3x squared is 0 over 0 still. Because secant of 0 is 1, right? Okay, so it's still in the 0 over 0 form. I could check to see, is there something I could do algebraically to simplify this? Not really. So instead of trying to simplify this, let's just apply the rule again and see what we get. Although I see with the next iteration of this, it starts to get a little complicated, because now when I take the derivative of secant, or secant squared in this case, it'll be 2 times secant x, so that's taking the derivative of the square on the outside, times the derivative of secant x, which is secant x tangent x, minus 1 is a constant, so the derivative is 0, so we're just left with, and then downstairs, 6x. Okay, so that's after our second application of the rule. Let me see, if this simplifies a little bit now, we can perhaps try and work it out from here. We've got 2 secant squared tangent in the top. And then just 6x in the bottom. Okay. Well, what I notice here is just from observing it as it is, there isn't any obvious things I can do to simplify it algebraically. Because the limit as x goes to 0 of secant squared is 1, and then tan of 0 would be 0. So actually we'd still have the 0 over 0 form here. But if you're a little bit tricky, what you might notice is that I could section off some of this stuff here. Because if I look at tan separately from this stuff here, well, tan is actually sine over cosine. And so sine x over x, we know goes to 1. So I could just do a little bit more manipulation here. So I got 2 secant squared x over here. This would be sine x over cosine x. Here I'll put the cosine x down here. And then this is sine x over x. Now I see, actually, if I look at these two pieces separately, this is going to go to 1. And then what remains over here goes to, let's see, actually the 2 over 6 reduces to 1 over 3. And then secant squared and cosine both go to 1. So we're just left with 1 over 3. Okay. So you notice that here, even though it was in the 0 over 0 form, you could have kept going with L'Hopital's rule. But actually, in this case, that might have sent us down the wrong path, because if I were to do another derivative, it's going to get a lot more complicated. Of course, I would have to use the product rule and some chain rule all mixed together. So it might make it a little bit more complicated. But the nice thing is then I would know that would be my terminal step, because then I would just have a constant in the denominator, so hopefully after that step I would be done. But here it's just kind of worth noting that, rather than continuing to differentiate to get one more iteration of L'Hopital's rule, we were able to work around it a little bit. Here's another example where the limit as x approaches pi from the left, sine x over 1 minus cosine x, will be in an indeterminate form again. So let's think about here as x approaches pi from the left. What happens to sine? Well, sine of pi is 0. Cosine of pi is -1, right? So this will be 1 minus -1. Now it's not actually in an indeterminate form. So if you're careful, we actually don't need to use L'Hopital's rule. In fact, we should not use L'Hopital's rule here, because this gives us 0 over 2. So we know this will be 0. That's the answer, right? But if we didn't check, so my warning here is, if we didn't check, you might have accidentally done L'Hopital's rule. So if you try L'Hopital's rule here, you'll get an error. You will get an error. Pretty bad one in this case, because let's see what happens when I take the derivative of sine. We get cosine, and then when I take the derivative of 1 minus cosine in the denominator, I think we just get sine. So taking the limit as x approaches pi from the left in this case would give me -1 over 0, right? Something that approaches sine approaches 0 as x approaches pi. Approaching it from the left here, so we would actually get something that would come out to be infinity. So you would get a very different result than what the correct answer would be. So that's my warning, is to be extra careful. Make sure that you can apply. Here we were not able to apply the rule. Here the L'Hopital's rule does not apply in this case, since it's not in 0 over 0 form. So that we always have to check.